Hoctor. And good evening. My name is John Hoctor. I'm Assistant Chief Fire Officer with Tipperary Fire and Rescue, and I want to welcome you this evening to our occasional webinar, Ventilation in Dwellings, a review of Technical Guidance Document F and Supplementary Guidance. I'm going to hand you over to Dave Carroll, Chief Fire Officer, Tipperary Fire Service, to officially open the webinar.
Good evening, everybody, and I'm delighted to be here to open this webinar this evening on Part F, the review of TGDF. So dealing basically with ventilation in buildings, in dwellings, I think is the focus tonight. I just want to thank Martin and John for pulling this one together. It's a really important topic, you know, and it's going to be into the future. Maybe 20 years ago, Part F, we, in all fairness, probably didn't take it that seriously. The danger is that there's a temptation not to take it as seriously now, but really what we're seeing is with the level of air tightness in buildings now, and I know it from my own personal experience, it's so important to get the ventilation right. The problems that can brew and fester with inadequate ventilation are, they're scary really, you know. There's all sorts of implications for air quality, for the health of the occupants, which ultimately is what building regulations are about. It's about health of the occupants as much as anything. And it'll impact on the fabric of the building over time as well. So look, the days of the hole in the wall have, if not quite disappeared, they're fast disappearing, and we're into much more innovative, I suppose, and modern solutions to the ventilation issue, and it's something we have to get right, you know. And as the regulators, we're bound to make sure that it is right. Certainly in Tipperary, we take it very serious. Ventilation is one of these ones now. We take it serious, every bit as serious as fire safety and the other ones, because I think through the work of Martin and John, we understand just, you know, when it goes wrong, it can be quite a serious issue, and quite a difficult one to go back retrospectively and solve, both difficult and expensive. Anything that's difficult in this game is typically expensive, and that's why we need to get it right. So look, I'm delighted to see so many on it. It shows the commitment you have to the building regs and to getting things right. So, and that is the experience we have certainly in Tipperary. I know we have others from outside Tipperary, and you're more than welcome as well. So look, with that, I'm going to hand you over to Martin and John. I know they have a busy evening. I would encourage you make use of the two lads here this evening. They're experts in the field. And if they don't have an answer for you tonight, they'll certainly get back to you with answers. It's in our interest that, you know, we want to hear what the problems are on site, what you're finding, where the difficulties are, where the barriers are, the obstacles. Share them with us, and we'll do as best as we can, you know, and look, we're all working to a common purpose here to make buildings better, safer, healthier for the people that put their hard-earned cash into them. So over to you, John. I think you're kicking off, and Martin. So again, thanks very much, guys.
Thanks, Dave.
Okay, thanks very much, Dave. So I want to start the presentation, I suppose, by echoing Dave's acknowledgement of your commitment to the quality and compliance with the regs by your attendance here tonight, and to say that we appreciate your attendance. The agenda here, a bit of background to where we were with regards to buildings, a little bit around building physics, not too detailed, and then outlining what the regulations are and the guidance documents. Then I'll hand over to Martin, who will go through the different types of systems, the common defects.
John, also, just before we go too far, did you try sketch a note or something on the presentation, because it's shown up there on the screen? If you can delete it off there just to clear it.
See, can I?
Just on the annotate there, head over and hit the eraser button. Yeah.
Can I reshare here again? Okay.
Yeah, it's perfect, John. Thanks.
Okay. Thanks, Martin. As I said, building physics, the regulation and guidance documents, the main type of systems, which will be outlined by Martin. What are the common defects? And then finally, the requirement that's in the guidance document now that actually every ventilation system must be validated. And that ventilation validation has to be independent of the installer. So before I get into the actual presentation itself, just a quick note to say that we run these occasional webinars in terms of building regulations. We try to do them once a year. Last year in 2023, we did one on Technical Guidance Document B, fire safety in dwellings. The link to the presentation is here. And just to note that actually, you know, all the regulations work together. So work has been done for compliance in Part F. If you're doing openings in terms of fire resisting construction, then you need to comply with the actual outlined requirements that are in the consolidated guidance in this presentation. The other item we want to do is to go along and acknowledge the construction sector and its role within economic activity within Tipperary and the wider Irish economy. The document on the right, on the left there, is a document published by the department looking at the capacity and performance of the sector in 2022. One of the figures within the actual document outlined there was over 160,000 people working in the sector in first quarter 2022. That number probably has increased at this stage, right? But what's of note is that actually the number of small and medium enterprises that are working within the sector. And that's reflective of what we find within Tipperary. So every town and village in Tipperary are small enterprises giving valuable employment for the people of Tipperary, but also supporting local community in terms of drama, sports and social activities, right? And what we're looking to do within the Building Control Authority is to go along and support and help those firms flourish and develop. So a bit of background, if we go back to the 1970s or earlier, I've put up some pictures there of standard bungalows or terraced houses. They were masonry construction, timber joist, concrete tiles. And as you can see here from one of the actual air tightness presentations, they were leaky dwellings, right? So there was lots of opportunity for air to kind of infiltrate from the outside through windows, through doors, through the wall construction, the floor construction, the roof construction, the chimney construction. So the heat sources within those buildings were solid fuel, maybe a cooker or an open fire. So the chimney acted as essentially a big vent and a suction, particularly during the colder months of the year, pulling air out of the dwelling, and then air was coming back in through the actual windows or the wall constructions. Wooden floors, air bricks or vents in the walls, single glazing wooden frames, no airtight junctions. And then possibly then in the colder months of the winter, people can remember back to the LPG super sayers or the 2-bar heaters. And there was no radon barriers, right? So this is all kind of very simple construction going back to the 70s and maybe the 80s. So in terms of those buildings, there was two effects that was giving you air movement within the buildings. One was called the buoyancy effect and the other one was called wind pressure effect. So if you look at the actual slide here on the right-hand side, it outlines the buoyancy effect. So if you take the example of the hot air balloon that we've seen in pictures, as you heat the actual balloon, the balloon rises. In the case of a house, the air rises, the hot air rises. And in a leaky house, that air ventilates out through the actual roof construction or the window construction. As that air ventilates out, other air is actually sucked back into the actual dwelling, and that creates air changes within the dwelling. The other effect then is the actual wind pressure effect on a dwelling. So this is a westward facing building. Okay, the prevailing wind is coming in from the western side. That creates a vacuum on the west elevation of the actual dwelling. That sucks air into the actual dwelling, and then that air is pushed out on the eastward or lee side of the dwelling, again giving you a uncontrolled but lots of air changes within the actual dwelling itself. So we've changed, we've gone to air tightness for all dwelling construction. And again, just a bit of history up to 2002, there was no mention of air tightness within the Irish construction regulations. And why are we doing that in 2024? So we're preventing moisture-related building damage, particularly in timber frames, prevention of drafts and cold feet, prevention of high heat losses due to infiltration, improving sound insulation, and improving air quality. because we're not getting radon on the ground. So that links back into the next slide here on the radon barrier. And I suppose the interesting fact is that a lot of us are very, very conscious of sunscreen during the summer months because of the possible impact of skin cancer. But the numbers up here suggest that the total radiation that we're exposed to as an individual in Ireland, we get 56% of that radioactive exposure from radon. All right. About 350 cases of lung cancer a year linked to radon. And that happens whether you're in a high radon area or low radon area. All houses that have been built over the last generation or so, they all have a damp-proof membrane. Okay, and then in high radon areas, that membrane has to be replaced with a radon membrane. All of the houses have to have a radon sump, right? That radon sump is only effective when the fan is put on it. So in terms of actually the sump being there and having an impact on radon, that doesn't make any difference until the fan is put on, and then it creates a negative pressure and stops radon infiltrating up into the house itself if the radon barrier is not effective. Since 1998, all dwellings that have been built in Ireland, nearly 30 years at this stage, have to have a radon barrier, not a damp-proof membrane. And you can see here in Tipperary, a lot of Tipperary is within the actual red zone or the high zone area. And the housing reference level for radon is 200 becquerels per metre squared. Testing of radon is very simple to do. Costs about €50 to go along and get a radon test kit from the NSAI. And then essentially, if we don't have a proper install, the homeowner can very quickly tell us, I'm in trouble. So the other point that's happened in terms of regulation is we've now gone along and we're definitely building airtight in the 2020s. If you go back to the actual noughties and 2010s, the whole concept of an airtight house is very new on building sites. And you can see here a notice from that era showing about actually no drilling, chasing or cutting without consulting an airtight supervisor. Today, the concept of an airtight membrane within the whole building envelope is part and parcel of what we do in terms of dwelling construction. Some of the pictures here show particularly around frame construction where you've got the membranes, you've got the tapes, and again, if you've got OPEs, you're running tapes around the actual OPEs, so you get good air tightness. And this here is some of the actual caps for downlighters being taped in, okay? One of the issues I want to bring to your attention is the ease at which the homeowner post-construction can go along and check whether good quality work has been done. You can now buy one of these thermal imaging cameras for about €200 or thereabouts, okay? And very quickly you can see if there's trouble in terms of the actual light tunnel here on the actual building. So the blue areas here represent thermal bridging, and that's either as a result of actually poor quality installed in terms of insulation, or there's actually a diminution in the air tightness, and we're seeing airflows, which is resulting in the actual the blue areas, which is reduced temperatures. So I suppose our concern as a regulator is that what we don't want to do is be getting pictures in from building dweller owners saying, I've got a problem, because when the problem comes into us, we're going back to the building and actually asking where the issues are. And as Dave mentioned at the start, resolving this subsequently is very expensive. So in terms of building physics, it's not going to be a long run through it, okay? But largely, you're heating the internal of the buildings here, okay? The external temperatures are lower, okay? And then heat is migrating from the inside of the building to the outside of the building. We're putting in airtight membranes, but those membranes will allow some migration of moisture across the membrane in certain cases, okay? One of the key issues that we need to be aware of, okay, is that if there's a cut in the actual membrane, okay, that's 1 millimeter wide and 1 meter long, that'll allow 300 mils, 1/3 of a litre of moisture to move from the inside of the dwelling into the actual cavity. And particularly with frame construction, that's an issue. I suppose just in terms of frame construction, when we go out and do building control inspections here within Tipperary, we're finding definitely a transition away from masonry construction towards frame construction. And last year, about 50% of all dwellings that we had submitted in commencement notices were either frame construction, primarily in terms of timber frame. So if we're seeing these 300 mils of water a day moving from the house into the timber frame, Okay, you're going to see long-term condensation and possibly mold growth, and maybe a structural issue within the actual timber frame itself. So in terms of preventing that, we don't just do good construction, we actually test that the construction has been effective. The blower test is called a Q50 test, so 50 pascals of positive pressure is blown into the house. And then we come up with a measurement of the air leakage rate based on the actual square meters of the external envelope. So the unit of measure is meters cubed of air per hour per meter squared. And the maximum limit for a dwelling in Ireland right now is 5 meters cubed per meter square per hour. And then if we're under 3 meters cubed per meter square per hour, then you have to have mechanical ventilation. So again, natural ventilation, there's a very narrow band in which you can actually put in natural ventilation. So in terms of ventilation, what are we trying to do? We're trying to change the hour, change the air within the dwelling on an hourly basis, okay? And essentially, air changes is making sure that the actual air volume in the room is changed and mixed with air from the outside. Why is that important? If you have too many air changes per hour through infiltration, then you're losing air that you've paid to heat, okay? And it's not very effective, and it all creates draft. If the air changes are too low, your air becomes stale, and you get a buildup of humidity, toxins, viruses, and also carbon dioxide, which is a leading indicator. And I'll talk about that in a few minutes later on in the presentation. One of the key issues is moisture within dwellings. You know, as any of us sit inside in a house on a daily basis, as we breathe and as we perspire, we release moisture into the atmosphere. So as I sit here again making this presentation here today, as I breathe in, I'm getting oxygen, and as I breathe out, I'm exhaling carbon dioxide as well as moisture from the actual my own body. 1 kilo a day is what somebody emits if they're staying inside in the dwelling. If I take a shower during the day, I'll actually allow between a half kilo and a kilo of water to enter the air from the shower. 0.25 kilos if I do the dishwashing. 0.24 kilos if I actually cook. And then if I do a wash in the washing machine, okay, and assuming that I dry the actual washing machine load inside, okay, a total of 3 kilos could be emitted into the actual dwelling itself. And the analysis that has been done by some of the actual humidity experts is that a 5-person household could put 10 litres of water into the air every day. And to put that in context, that's 20 pints of water. If you line that up and said, we're going to throw that into the air, it's a lot of water in the dwelling. And that's why ventilation is so important. So if we have a dwelling and we don't have good ventilation, okay, then we end up with condensation inside the dwelling, and we also end up with mold. I'm not going to go down through this slide here line by line, okay. One of the issues though is that actually, whilst the mold can actually come up and be removed by using household cleaners such as bleach, okay, it'll still come back again. And the head issues for the occupants in terms of respiratory problems is at this stage proven. Right? So it's going to become a key issue as we move forward. So this is a slide I put together, which is a background slide based on some information we had here within the administration building in Clonmala Fire Station. The administration building is actually structures such as the internal administration office, which is used by 3 admin people, has no external window. So there's no natural ventilation within the external or internal administration office. When we measured the humidity levels inside the office with the 3 people in there, we found they were very high. So we put in a continuous minimum extract ventilation system into the office itself, right? We also invested about 150 euros buying one of these detectors, which measures temperature, humidity, and carbon dioxide. So taking the first one here, which is carbon dioxide, and carbon dioxide is a leading indicator of air quality within a room occupied by 3 people. If you don't have ventilation, the carbon dioxide levels will go up. The recommended level for carbon dioxide in a room is a maximum of 1,000 ppm. And you can see here, as we go from the 2nd of October to the 5th of February, you can see the variations on a 12-hour basis, 12-hour average basis of carbon dioxide levels over the 4-month period at around 500 ppm average, but going up and down depending on the moving averages. The second output from the sensor, which is again Wi-Fi enabled, okay, is looking at the temperatures, okay. So the recommended temperatures are 19 to 23, and you can see the upper level and lower level are displayed here by the software. The red line indicates the actual temperatures in the office over the 4-month period. And this is taking data from Met Éireann for the Clonmel area. And you can see the outside temperature dropping down during December, January, whilst we're still keeping the room temperatures up within the recommended levels. And the last one then is the humidity, which was the reason why we put in the minimum extract ventilation. And now we're now measuring it and seeing, are we achieving the actual humidity levels? So the maximum humidity levels within inside an office or dwelling is 60% humidity, and the minimum level is 40% humidity. The red line represents the humidity within the internal office within the Clonmel administration building. And you can see that we're, once we turned on the actual ventilation system, we've never exceeded humidity levels within the office areas from the period of the middle of October to the 5th of February. And you can see the outside humidity levels again being calculated from Met Éireann are varying depending on the actual weather and the external temperatures. So the point I'll make is that when we go along, we build new dwellings, okay? And if somebody has got a concern in terms of air quality, it's very easy for them to go along and buy one of these sensors here for €150, Wi-Fi enable it onto their phone, pick up that by the analysis that I've shown here, and either go back to the actual builder or go back to ourselves as a subject of complaint. And the resolution of that type of non-performance can be expensive if the actual installation design has been done correctly. So the law, right? Okay, so a bit like seatbelts, we've got laws in Ireland that have been put in place under the enabling legislation of the Building Control Act from 1994 to 2014. And Part F is the ventilation regulations being signed into law by the Minister. And what does Part F say? It says that adequate and effective means of ventilation is provided for people in dwellings. These should be provided by limiting the moisture content of the air within the building, so that it does not contribute to condensation or mold growth, and limiting the concentration of harmful pollutants within the air. So again, very, very simple, right? Kind of, and again, not something that anybody can argue with in terms of a reasonable regulation for the health of the occupants within the building. The question is what's adequate, and we'll go through that in terms of the guidance documents from Martin later on in the presentation. And I suppose the key issue here, it applies to new construction, to extensions and to retrofits. So as we go along and do any of those works, we need to make sure we comply with the actual Part F requirements for adequate and effective ventilation. How do we do that? Part F has a guidance document that runs to about 51 pages that goes down through how to get adequate ventilation for the different types of dwellings and the different types of systems. That Part F document has to be read in accordance or in compliance with Part L, which is the actual air tightness requirements and the energy saving requirements for dwellings, okay? And as I mentioned at the start of the presentation, there's also ancillary guidance, which is the installation and commissioning of ventilation systems. And the key point to note here is that the installer cannot go along and do the validation of the actual system, a bit like the main dealer can't do the NCT. You've got to bring it to the NCT centre. On top of that, there are acceptable construction details to make sure we don't get thermal bridging in the actual installation of air tightness or insulation within the dwellings, okay? And again, those thermal bridging acceptable construction details are detailed in ancillary guidance that's available on the website. So that concludes my side of the presentation in terms of giving you the background and the actual legislative imperative. I'm going to hand over here now to Martin Moore, and he'll bring you down through the actual detailed technical advice.
Ideal. Thanks, John. Okay, assume you can see my screen there now. So just to reiterate some points John said there. So like the indoor air quality in buildings and particularly in dwellings now is becoming more and more important than possibly it ever has in the history of regulations or buildings in this country as we progress to more and more airtight buildings, right? And even if you take the radon part of it and having, you know, if you had your old drafty building, the radon was ventilated out of it pretty easily. The more airtight building you have, and if God forbid there was a rip or tear in the radon barrier somewhere, and all that radon comes into the building, like there's about 250 deaths each year that are linked to radon from lung cancer. You know, you put that in perspective, we had 184 road fatalities last year in Ireland. So it is something to take very, very seriously. And indoor air quality, it has the potential to become the next micropyrite scandal because of how serious it is and what we're talking about here. And what we are finding from doing building control inspections is it hasn't been taken as seriously as it possibly should be, particularly where natural ventilation is still being used. And I'll go through that in a little bit now. But I suppose firstly, just to kick off and go through the three main systems that are detailed within Technical Guidance Document F. So we have three systems in Ireland that are recognised as adequate to provide ventilation to dwellings. So the first one is our continuous mechanical extract ventilation, or and that can either be demand controlled or with our standard background vents. Probably the most common system we are seeing now, thankfully. Some people do spur the extra few pound for a mechanical ventilation with heat recovery. Again, another great system. Does have its downfalls and its pros and cons, and I'll go through that and some common non-compliances we come up with it. And then lastly, they did, for some reason, leave natural ventilation as an option within Technical Guidance Document F 2019. The problem with natural ventilation with the intermittent extract in your bathrooms and in your wet rooms is you have a very, very narrow band of air tightness to try and achieve. You're trying to hit a value somewhere between 3 and 5. Now, I have done a few building control inspections on a few ICF developments in recent years, and while I was out there, they were proposed as natural ventilation. The science author and the builder were warned at the time, look, just be warned, if the air tightness test results come into us and they've dropped below 3 with this natural ventilation, I will be looking for some form of remedial works to make sure that the house is adequately ventilated. And unfortunately, what happened, it came to CCC stage, submitted their air tightness test results, and lo and behold, they achieved 1.8 to 2.5, all well below 3 with natural ventilation. So that house was never going to be adequately ventilated. So what had to happen then was we had to take enforcement and push it then that a mechanical system had to be installed to ensure that adequate ventilation was provided to that building. It's something that if it isn't done right, it will fail very quickly because the tenants are going to have condensation inside in their houses. They're going to have mold growth. So it's something that will be very apparent to them if there is issues. The overheating side of it as well is also quite common. So, with continuous mechanical extract ventilation, once you hit the backstop value below 5, you're fine. Mechanical ventilation heat recovery, backstop value of 5 on the air tightness, and you're fine. But with natural ventilation, you have to get your air tightness between 3 and 5. And I'll be honest with you, I don't think we're setting the industry up for success in that because it is such a difficult target to try and hit. So just something to very much be aware of. So with our continuous mechanical extract ventilation system, we'll have a centralized extract fan, usually placed above in an attic or a plant room or utility room somewhere, pulling air from all the wet rooms, pushing it to the outside, putting the whole house in negative pressure, and pulling air then from background vents within either the walls or in trickle vents in the windows. So just some pieces to be aware of. If the replacement air is done by humidity controlled inlets, as in it's a demand controlled ventilation system, that has to be designed by a specialist. The other thing to be aware of there is that the flow rates that are detailed within Technical Guidance Document F, they will not be achieved by a demand controlled system. So any demand control system that is to be used has to have an Irish Agamon cert to prove that it is going to do the job that it has to do. Outside of that, you are really out in a limb in terms of having any sort of certification for it. And again, the system may not work as it's supposed to do. So with any demand control ventilation system where you have the inlets are humidity controlled, make sure it has an Irish Agamon cert. And as far as I'm aware, there is only actually one system on the market in Ireland at the minute that has an Irish Agamon cert. So just be very careful about any client that you're dealing with or builder that's trying to import from another country. If it doesn't have the paperwork, you're not setting yourself up for success. Any of the inlets should be about 2 meters above the floor level, and make sure that they are located away from the doors in the room. You have to ensure you have a sufficient rate of air transfer throughout the room. If the inlet is right beside the entrance door to the room, you just get short circuit and the air will just go straight out under the door. the big downside to the continuous mechanical extract ventilation is you are pulling heated air from the building and dumping it outside. There's no heat recovery in this system. It's pulling the air straight out to the outside and dumping it out there. On the other side, it's a bit cheaper than MVHR, and in fairness, in Ireland, we don't tend to get the extremes of temperatures that you'll see in some of the Scandinavian countries that would go with MVHR more commonplace. So look, it has its pluses and minuses. If we're not going with a demand control system and the CMEB is ran with background ventilators, like a hole in the wall, basically, or a hole in the wall, or trickle vents, you have to have at least 2,500 millimeters squared in each room, except for wet rooms. So that has to be what has to be achieved. Yeah, you can have more than that, but you cannot have less. So just be wary of that, because depending on the size of if you're going with trickle vents in the window, like, to put that in perspective, that's probably a 400 mil wide trickle vent in the window. So if you put in a 300 millimeter wide trickle vent or 250 wide trickle vent, that's not going to achieve that ventilation rate or the equivalent area required. MVHR, again, quite a common system. We're seeing more and more. The inside air is put through a heat exchanger, preheated, and outside air is then put through the heat exchanger and put into the room. So just be aware that intake and exhaust terminals should be located on the same facade to reduce wind pressures interfering with it. So the image probably doesn't do it justice, because by rights the inlet and the exhaust should be on the same facade, so that whatever way the wind acts upon the building, it doesn't cause an issue with short circuiting. The downside with MVHR is, look, it's a more expensive system, and there's a lot of duct runs to try and insulate and airtight and make sure that all the junctions are done right. And again, as a science certifiers and builders, you're trying to pick up on that and make sure that all that work is done right. Sometimes you're going to be relying on an ancillary cert, but in majority cases, you're going to be the one checking it. And then the downside, then I suppose the big one, the big elephant in the room really, is the natural ventilation with a specific extract ventilation. So what that is doing, as John said, it's looking at natural air buoyancy, and it's exploiting the pressure differentials created by wind or temperature. So it is not equal in every house. It is very much a kind of almost a guess game, really. I live in the shadow of the devil's bit. If the wind is blowing a gale, the house is well ventilated, but it gets cold. In a hot summer day when it's dead outside, very little air movement inside in the house, so it's quite stuffy inside. So it isn't a perfect system by any means, and it does require, so very much proceed with caution with a system like this. So the vent ops, they'll act as both inlets and outlets. They're doing the same thing, all depending on which way the wind is blowing, and the air temperature outside. And we do provide local extract fans to wet rooms. So you would have all probably done that, axial fans or the centrifugal fans, and we'll talk about that a little bit. But the downside to this system, the effectiveness really, really does depend on the exposure of the building. So Table 3 of Technical Document F will talk you through exactly what general ventilation you require for each background ventilator. Okay, so just something to highlight, the habitable rooms typically 7,000 millimeters squared, your kitchen 3,500, utilities 3,500, bathroom 3,500, and if you have a toilet under stairs or something like that, 3,500 as well. Okay, just with regards to equivalent area. So this is something that, again, that is still sometimes gotten wrong based on who bought the face covering for the inlet. Okay, equivalent area and free area are two different things. So a free area is basically just the geometric opening of all the openings inside the louver or the vent, or the face covering for the vent, the hit and miss vent. Whereas equivalent area is actually a scientific test whereby they've tested the airflow through an aerodynamic test to determine how much air actually passes through that ventilator. So TGDF is written in terms of equivalent area. So if you are using free area, you have to increase your values that you need to achieve by 25%. Okay. Other thing to be aware of if you're using natural ventilation, so your minimum ventilation rate should be 42,000 millimeters squared plus 7,000 millimeters squared for every 10 meters squared above 70 meters squared. So a little calculation to be done. You add all that up, and then you divide it then by the number of habitable rooms you have with inlets or vents in it, and you may need to bump up the number of inlets as required to hit that ventilation rate. Something as well, again, with natural ventilation, if you're providing extract ventilation to kitchens, utilities, or bathrooms, or WCs. So for your kitchens, you need 60 liters per second, or 30 liter per second if the cooker hood is non-recirculating, as in it's ducting straight to the outside. 30 liters a second for utilities, 15 liters a second for bathrooms, and 60 liters a second for WCs. something to be aware of is that not all the fans are equal out there on the market. Okay, some fans perform far better than other ones. So the centrifugal fan is your Rolls Royce of extraction fans. Okay, that achieves a significant extraction rate in any bathroom. The downside to taking Guy's document F with regards to providing the extract rates there is it doesn't take account of how big the room is. So liters per second, it's just a general number. So if you take a your bathroom there at 15 liters a second, your standard axial fan achieving about 54 meters cube per hour flow rate will achieve that 15 liters per second. But that fan might not actually be adequate enough to clear the condensation that's generated by a shower in a large bathroom or by a large bath. So sometimes, and again, it's just to be aware of if you ever call back to a house where the client is complaining that the bathroom is full of condensation the whole time, even when the extract fan is running, it's typically because the fan is not big enough to actually ventilate that room. The room is too big. So just something to be aware of. A nice rule of thumb there for you, 1 liter per second is about 3.6 meters cube per hour. So if I have an axial fan, which will typically achieve, and most fans are kind of sold with the meters cube per hour as opposed to liters per second. So sometimes you just have to convert it. But your standard axial fan will do about 54 meters cube per hour. So that's about 15 liters per second. But if I have a bathroom that's, about 12 meters cubed, and I need, like, if you go to any of the CIPSA guidances, they'll recommend about 6 to 10 air changes per hour for bathrooms. So at that, I would need 72 meters cube per hour. So by rights, I actually am not achieving a good ventilation rate in that bathroom, even though I have actually complied with Part F. And as I said, Part F, prima facie compliance, but it's just something to know, because it can happen that a client might come back to you saying, look, I'm unhappy with how this bathroom has been ventilated. What's going on here? That's most likely the case. Now, with our mechanical extract ventilation systems and our mechanical ventilation with heat recovery systems, 10 Guinness Document F has a general ventilation rate that has to be achieved. Okay, there's two methods that you can apply. So the first one is 5 liters per second plus 4 liters per second per person. So that's what the general ventilation rate of the system should achieve. Or you do it 0.3 liters a second per meter squared of internal floor area. Whichever one of them is greater, sometimes you're going to have a bigger house with less people. So depending on which one it is, that's the one you have to go with, whichever one is the greater. So if I take a typical example there for a 3-bed semi-D, if I have 2 bedrooms and a single room, so that's 5 persons, 5 liters a second plus 4 liters a second by 5 people. 25 liters a second is what the system has to achieve as a general ventilation rate. Whereas and that's taking the per person route. If I take it that the 3-bed semi-D is 120 meters squared and it's 0.3 liters per second by 120 meters squared, 36 liters a second. So that system actually now has to achieve 36 liters per second, as it's the higher number. So something just to be aware of. Now, demand controlled ventilation systems, your mechanical extract ventilation with demand controlled inlets, that will not achieve these ventilation rates. I can guarantee it. So any demand controlled ventilation system that is put in has to have an Irish Agriman cert to prove equivalency to 10 Guinness Document F. Okay, so just be very wary of any system that is pulled out from that. Something else as well to be aware of that sometimes comes up and we do get queries on is positive input ventilation. Positive input ventilation systems, basically they put the whole house under positive pressure, but what it's doing is it's driving all the moisture and condensation out through the inlets. But if you have any issues in terms of a break in the air tightness membrane anywhere or vapor control layer, that's where all the moisture is going to be pushed to. So PIV systems are actually not prescribed in Titan Guidance Document F. They are in the UK, and there is BBA certificates that I have seen for them, but you will not have an Irish Agriman certificate for it. Not a good system, in my own personal opinion, for this country or in general, because as I said, you're pushing moisture into the structure of the building and hoping that it goes out through the outlets and the inlets, putting the whole house under positive pressure. So either DCV, it's Irish Agriman cert, or you're going with an extract system. So in addition to the general extract rates, you also have boost ventilation rates. So just again, something to be aware of, Table 1 and Table 2 of 10 Guinness Document F, your system also has to be able to achieve these boost rates. And look, I won't go through it too much with you because I'm conscious of time and I want to go through the common non-compliances. But again, make yourselves very aware with these systems. If you are offloading it or to an outside company where they're providing the calculations for you, always double check. You're the one working on the building, you know it better. Just double check them, and using these kind of tables will help you to do that. So John touched a little bit on some of the guidance available, and I'm going to push it out a little bit further and give you some other documents to refer to. So you have Technical Document F 2019. It's our Bible in terms of ventilation in this country. You follow that to the letter of the law, you're prima facie compliant with requirement F1. You've complied with the law effectively. On top of that, there's some additional guidance out there to assist with that. So you have the installation and commissioning of ventilation systems for dwelling, achieving compliance with Part F 2019. That's also available from the same website as TGDF, the Department of Housing. You have the SEAI's Code of Practice for mechanical extract ventilations and MVHRs. Again, a very good document, gives you a very good kind of rundown of what you need to be aware of when installing those systems. SR 54, your energy retrofit manual, again, some ventilation criteria in that. Again, with retrofits, if you're doing a significant level of insulation and air tightness, ventilation has to be considered, and it has to be taken very seriously, and it has to be calculated. It can't just be forgotten about and we just up the insulation, because what will happen is condensation and moisture have to go somewhere. They will go into the fabric of the building if it's not ventilated correctly. BS 5925, it's been around for donkey's years. It's referenced in Technical Guidance Document F. It's referenced in Technical Guidance Document B as well for natural ventilation. It's a very good code of practice for basically designing natural ventilation from first principles. So it's not looking at the likes of TGDF and the 7,000 millimeter squared per flow rate. It's looking at what's the floor area of the building, what's the height of the room, how many people are in the room. Based on how much condensation could be delivered, this is how much ventilation rate you need. Kind of basically, as I said, going back to first principle engineering of it with that. So it's a very good document if you're ever looking for trying to design natural ventilation systems. And then there's BS 5250 as well, which is another great code of practice for the control of condensation in buildings. Two very good documents there that you should be familiar with. Okay, so on to the common non-compliances. So the first one I like to kind of call the Temu effect, or the Alibaba effect, whatever way you want to go with it. So buying cheap ventilation products, or if the client you're working for has picked out the ventilation fans themselves, whether it be from Screwfix or Temu or wherever they found it, be very aware of any system being brought in from any other country. They have to be certified to ISEN 13141. So what that standard is, it's a harmonized European standard for basically testing the performance of ventilation products. So it'll test what the airflow is through it, how the system works, and is it fit for purpose. So any fan, any ventilation product, whether it's a louver, a fan, a diffuser, it has to be tested to this standard, and you have to have certification to prove that. There's 11 parts to cover everything from fans to inlets to outlets to the whole lot. So just again, be very aware of that. We have come across products that have been installed that did not have any certification, that were bought cheap, and they obviously don't work. They're not performing to what they should be doing. Another common one for us is this lovely white ducting that I'm sure you're all very familiar with, the flexible ducting. So two major issues here, right? One is the length of it, and two is the fact that it's uninsulated. Okay, it's above in the cold attic. We've 300, 400 mil of insulation in the attic, and we've this lovely duct that's taken moisture-laden air from a bathroom to the outside. Okay, so first of all, with regards to the length of it, with axial fans, which is our standard kind of, square plate fan, the max run of any ducting out of that, if it's flexible, is 1.5 meters. Can't be any more than that. If it's more than that, you have to use either rigid ducting or something more appropriate. For centrifugal fans, which is my middle picture there, my little black, the little black kind of box guy, that you can get up to 6 meter of a run with the flexible ducting. Okay, but the ducting should be insulated. You either put your layer of insulation on top of it, or you buy insulated ducting itself. It needs a minimum of 25 mil at about 0.04 watts. So, your 0.04 watts per meter Kelvin, that's your standard kind of mineral wool insulation conductivity that you'd achieve. Has to be a minimum of 25 mil around it. Okay. You have heavy moisture laden air coming into it. What will happen is, particularly with my centrifugal fan here, as it's been brought up here into a roof outlet there, that will condensate inside in the duct itself, and the water will just sit in it and run back down and either burn out the fan or run back down into the dwelling. So something to be very aware of, and again, that we come across very common. that the bathroom is extracted up into the attic and the duct is just left there uninsulated. Poorly installed ductwork as well for MEVs and MVHRs. Again, very, very common. So if you have peaks and troughs within your ductwork, again, it's going to cause condensation and water just to sit inside in that duct. We don't want it in there. We want the moisture taken out of the building. So with any ductwork, it should be supported every 750 mil, or check with the manufacturer of the system because they might have a requirement that it's supported more often. Otherwise, it will peak or there will be dips in the ductwork as it's been laid out. Similar to my lovely white stuff, if the ductwork is outside of the thermal envelope, it has to be insulated. You either lay a layer of insulation on top of it, or you buy insulated ductwork, one or the other. So if I have that very complicated ductwork there in the attic brought to that mechanical ventilation system there, like that is very difficult to try and insulate that and do that correctly. Okay. The other thing to be aware of as well, and you see it there on the left-hand side picture and on the middle picture, any of the joints between ducts and diffusers or between ducts and the mechanical ventilation unit, they have to be airtightness taped and insulated. So very good practice there on the right hand side. You see all my junctions are taped with file-based airtight tape, and similar there with the one below it as well. So that's what you want to see and that's what should be provided. Now, again, I've mentioned this already with my ICF builds. Natural ventilation used with an air tightness result of less than 3 meters cubed, that will be a failure. I can guarantee it, whether it be a month or 6 months or a year, condensation is going to build up in the windows inside in the house. It's going to get mold growth. It's going to cause issues. The house is going to be overheated. It's going to be stuffy. It's not going to be well ventilated. So if that does happen, it could lead to significant condensation and mold growth, and it will require significant and costly retrofit measures. So you're either trying to retrofit a full mechanical extract ventilation system or a full MVHR system, which is going to cause difficulty because now you're looking at trying to run ducts here, there, and everywhere after the building has probably been fully sealed up with air tightness and the whole lot. Or you're looking at trying to retrofit a decentralized MVHR system. Just again, be very wary of these because these can be bought online for about €600 or €300 each, depending on the unit you buy. But really, you should be getting a specialist to supply and install them because they have to achieve the flow rates that are provided in Part F, and they all have to work together. So effectively, what the unit is doing is it's an MVHR system for each individual in each individual room. It'll pull out air at a certain rate once the humidity is reached. It'll go through a heat exchanger and then pull in air from the outside and ventilate the room. But you need your gap under your door, and all the system, all the units need to work together. They can't work independently. So again, it's specialist design, very costly. Another common one we see with kind of dormer conversions and room and roof kind of situations is natural ventilation used with a ceiling height below 2.4. Similar to my previous slide, you're going to get condensation and mold growth because the ceiling height is so low, and you just won't get the airflow rates through it. Okay, so you kind of have two options really here. You either calculate exactly how much natural ventilation you need, going back to first principles using BS 5925, or you have to put in mechanical ventilation in that area to make sure it's adequately ventilated. Okay, either way, you'll have to do something with it. You can't just leave it being unventilated. What I would just say, if you have gone below 2.4 meters minimum, which is recommended in Part F, keep in mind your minimum headrooms for safety and for accessibility. So 10 guys document K and B both say 2 meters minimum for headroom. So that's the absolute minimum headroom required for anything. Because you go below that and you're not in compliance with any part of the building regs. Once you go below 2.4, you're technically not in compliance with TGD F. So you're going out on a limb to try and figure out how do I actually ventilate this properly from first principles. So just be wary of it. Another common one we come across is the mechanical ventilation system it's been commissioned before the final joinery work has been done. So if the stairs hasn't been put into the building yet, or the kitchen cabinets haven't been put in yet, but the mechanical ventilation system has been commissioned, what's it going to be doing? It's pulling air through the system, particularly with MVHR, and it's going to completely clog up the filters before anyone has even moved into the house. Okay, so just be very aware of that, the timing of when these systems are actually commissioned and turned on, because if the carpenter comes in and starts creating sawdust and particulates inside, that's going to get all sucked into the system. And as I said, the filters would be destroyed, and the client is wondering, why is this system, why is my house so stuffy, and why is the ventilation system not working? And we've pulled out, your filters there, and they're actually clogged up to the last, because of the amount of dust created. So just be very wary of that. Another one that's a big bugbear for mine. We are designing and building buildings for people at all ages in life. Okay, if we are putting ventilation units above in the attic, out of sight, out of mind, how is the 65-year-old or 75-year-old couple supposed to get up there? Like, these things require maintenance. The filters have to be cleaned out. Some of them have washable filters, some of them have replaceable ones. Either way, they have to be done. If the unit is put above in the attic, how does anyone get access to it with any sort of ability issues to do it? And even someone, without ability issues, it's a pain in the arse to have to get up into the attic to clean out. And if it's up there, it will be forgotten about in reality, until the filters are completely clogged up and the system stops working completely. So it is a much better practice to put these systems down in the utility room or down in the plant room, somewhere like that, in the house, where they're easily accessed, can easily clean out the filters, and then you're not worrying about trying to insulate ductwork, because it's all within the thermal envelope as well. So the other thing to often watch as well is people put these systems in the attic space and they don't actually check, is the ventilation unit suitable for cold atmospheres. So check with the manufacturer of any system you're getting. If you are putting it in the attic, make sure that it is suitable to be up there. And secondly, what you have to provide is a walkway of some sort to that unit to allow maintenance for it as well. It can't be put at the back of the attic, where, if you look at my bottom left-hand picture, where I have no walkway to actually get to it to clean out the filters. So again, be wary of that. This one, it still is occurring, particularly with spotlights and with diffusers for MVHRs. So if I have an engineered joist floor, like what I have there in the image, any diffuser, any opening through that has to be fire stopped. So it's an intermittent collar on the ductwork as it goes through the plasterboard slab, or it's a damper kind of diffuser whereby it'll slam shut upon a fire impinging upon it. Okay, so just something to be aware of, that fire rated diffuser, it has to be installed with any metal web joist floor, has to be fire stopped. And just to recollect on our consolidated guidance that we have out there for 10 Guys Document B Volume 2, if you have a 2-story house, the floor has to achieve 30 minutes in terms of resistance and integrity, and 15 minutes in terms of insulation. And if it's a 3-story house, it's a full 30-minute fire resistance in terms of resistance, integrity, and insulation. So that has to be achieved. Any product picked for the diffuser, it has to make sure that it also achieves those fire ratings. The location of inlets and outlets. So if I've got an MVHR system and I have an inlet or an outlet beside a smoke detector, that's going to cause an issue. You're going to disrupt the air around the smoke detector, because it's either pulling air away from the smoke detector or it's pushing air towards it. So what will happen in a fire scenario is my smoke isn't going to be able to get to the detector because of the air movement of the diffusers. So if we go to the new fire alarm or fire detection alarm system standard, IS 3218-2024, just brought out there in September, it specifically says that any smoke or heat detectors should be at least 1 meter from any supplier extract air diffusers. So just again, make sure of that, because there is a common thing to kind of put the light beside the air or the extract diffuser beside the smoke detector, and they're all within like a meter of each other, or 500 mil of each other. So you have to space smoke detectors away from these diffusers, or vice versa, space the inlets and outlets away from the detectors. Another common one is the gap under the door. And again, I know this is probably an issue where you're handing over a house that just has a concrete floor, and there was a 10 mil gap under the door when you handed it over. Client comes along and puts in a carpet, and now my 10 mil gap has turned into a millimeter, maybe 2 millimeters. You have to make sure you have a 10 mil gap under the door, no matter what type of ventilation strategy you are doing. If it's natural or mechanical, a 10 mil gap under the door has to be provided to give you cross ventilation through the house. The whole house relies on the system working together. It's not a case of ventilating room by room. Even with natural ventilation, the background vent in one room is pushing ventilation throughout the entire house. So just be very, very aware of that. If the floor finish is not fitted, make sure that you make the owner of the house very much aware that they need to have that 10 mil gap, because it might be a case the door has to come off the hinges and we plane off 10 mil off the bottom of the door when they do fit a floor finishing. There is There is some guidance out there that says if the floor finish isn't fitted, that you should provide a 20 mil gap. I'm not a big fan of that, because if they provide a vinyl type floor, I mean, that's only going to be maybe 3 mil in thickness, and I have this big massive gap under the door, which is a particular problem if you've got a 3-story house and you needed fire doors. So this is a bit of an issue, and it's starting to kind of come right now. Fire doors, historically, they were only ever tested with maybe a 5 to an 8 mil gap under the bottom of the door. Some of the newer doors are being tested with a 10 mil gap under the door, and they are still achieving the target fire resistance. But it is just something to be aware of, that if you've got a 3-story house with fire doors, your FD20 doors provided to the stairs, make sure that you still have your 10 mil gap, but it cannot be any more than 10 mil. So it's a little bit difficult. It's a bit of a sweet spot to try and achieve. So just to be aware of that. Now, finally, I think, is our ventilation system not validated by a third party. And I know we are getting kind of a bit of pushback on this, because I 100% appreciate it is very difficult to sometimes get NSAI ventilation validators, because there just isn't enough of them in the countryside. I have talked with the department about this, and the attitude is kind of like, build it and they will come. So like the BER certs back in the day, any ventilation system being put in has to be validated. So we have to get in a third party NSAI ventilation validator to look at the scheme and make sure that the system is actually working correctly. For ourselves here in Tipperary, any compliance on completion certificate that is submitted for a housing development or a house, we look for the ventilation validation scheme now going forward. Okay, so just make sure that you have it lined up early in the project, because we have bounced back compliance on completion certs for not having that validation scheme or that ventilation validation scheme certificate for the houses. So just make sure it's in there. Okay, the system, the ventilation system, it's checked in accordance with IS EN 14134. You will get a little ventilation validation certificate, like in the bottom right hand side of the screen there, detailing the flow rates in each room and did the system pass or fail. Okay, so it's very, very important, has to be provided. It's required. It's a requirement under Technical Guidance Document F. So we are pushing it now with any compliance on completion certs submitted, and we can't accept it without it, because it is proven that the system is working correctly. Just because the guy who installed it has commissioned it, because ventilation has been taken so seriously, we need to have it validated. Any of the flows have to be validated. So just to conclude on that, and John, if you want to come in at any points there now with that. So ventilation, it should be a key priority of designers, particularly for any home that's achieving air tightness levels that are less than 3 meters cubed per hour per meter squared. Not all systems are created equally, and I would really urge anyone proposing natural ventilation, really approach that with caution. You're really trying to hit a target that's very difficult between 3 and 5 on the air tightness, and in any case, it just, with the modern day building, it is not going to adequately ventilate the house. You need to have a critical analysis of any proposed ventilation strategy at an early stage, and you need to be aware of what's going on. I wouldn't just farm it out and say, yeah, it'll be fine. You need to be able to do your own checks on it and make sure that it's been done right. And you see there from the common non-compliances that we are coming across, that things can go wrong, and they do need to be watched out for. There is some good guidance out there. Talk to myself and John if you're ever unsure of anything when it comes to any part of the building regs, not just fire. We cover everything. You're very lucky in Tipperary that you have a fire officer and a building control officer with the same hat on. So please do get in contact with us if you do have any queries or anything you're not sure of. We are here to help. We are more than willing to help anyone who asks for help. It makes our life easier in terms of the enforcement side of the house, and we want to promote a culture of compliance, not enforce our way there. So do talk to us. Be aware of the common non-compliances that I've went through. We will be sharing these presentations with you afterwards, and we will share the recording as well. But look, ultimately, ventilation systems in houses, they're not a DIY job. This is specialist knowledge and installation that is required to do this right. Okay, they have the potential to go very, very wrong otherwise, and it will be a legacy issue in the building if we don't get it right. So just take it very, very seriously. Don't be kind of pushing it off to one side and leaving it to chance for the system. So with that, I will thank you very much for your attention. If there is any questions, just throw them up in the chat there now. John, do you want to come in on anything?
Yeah, no, just want to acknowledge everybody's attendance here tonight. One of the points that I forgot to mention actually was that the approved housing bodies for social housing in the UK and in Germany are now start to use conditioning monitoring for their buildings. So what they're doing is they're putting in combined CO2, humidity, and temperature monitoring within each particular dwelling or apartment. They're linking that back up to their management systems, okay? And that allows them to go along and actually figure out, is the dwelling complying with the actual requirements in terms of ventilation and heating, or if there's any unusual occupant activities. So what happens in the UK and happens in the continent, you could see approved housing bodies doing that as well through here for social housing. So just to be aware of that as a possible long-term trend within the rental sector.
Yeah, exactly. Just there's two quick questions there on the chat. I might just cover them because we've got a little bit of time there now. So look, the first question there is just in relation to a 3-story dwelling with cross ventilation under the doors. I think I probably covered that. As I said, check that the fire door has been tested with a 10 mil gap under the door. It has to. You need a 10 mil gap for ventilation, but at the same time, the fire door can't allow any more than 10 mil. I have seen some fire doors tested up to 12 mil to give you a little bit of tolerance. But by and large, it is 10 mil that you have to get it. There is no requirement for a smoke seal at the base of a door of any fire door, so don't worry about that. Second one there, just regards to natural ventilation. So nobody's using natural ventilation anymore. Unfortunately, that's not the case. I wish it was, but they are. If you do hit less than or hit 3 on the air tightness test, it's not just a matter of adding holes in the wall until you get between 3 and 5. So just on that, we're talking about air tightness and ventilation. They're two different things. When you do an air tightness test on a house, they're blocking up all the ventilation openings. Okay, that's not part of it. That's testing the fabric. The ventilation then is putting holes back into it. So you adding holes will not decrease the air tightness of the building because the air tightness test was based on all the ventilation holes and any gaps basically closed up. Okay, so it's not just as simple as that. It's basically you're looking at either providing additional vents to get a required ventilation rate in accordance with BS 5250 or 5290. But the problem with doing that is you're going to over ventilate the house very possibly and make it very drafty. So the best system is go with a mechanical system and do it right. So with that, if there's any, I think there's
one last question there on ACDs for ICF construction. Typically, my experience has been that the agreement certs for the ICF would show very good ACDs for
the Agrimon certs for ICF actually have your psi values calculated for you if you go to the back of the Agrimon cert for any ICF. So they have the psi values, and in most cases, ICF actually performs better than what the ACDs do. The problem is you cannot use the 0.8 thermal bridging factor if you're not using the ACDs. So if you're using ICF, you can't use 0.8. You have to talk to the manufacturer to see have they worked it out for you and can they give you a thermal bridging factor, or you're actually working it out yourself based on the as John said, the details in the Agrimon cert. Just one there on spray foam insulation in Ireland. Is it an issue like in the UK? We're not seeing it as common here. I know there is issues in the UK in terms of people not being able to get mortgages and not being able to get insurance on it. There are Agrimon certs out there for it. Personally, I'm not a big fan of the system, but if it has an Irish Agrimon cert, it's demonstrating compliance with the building regulations. You can theoretically use it. Yeah, it has to be still fit for purpose though, so it has to fully conform to the Agrimon cert. There are open cell spray foam installations that do have Agrimon certs in Ireland. I still think most of them do require the 50 mil ventilation gap in the roof, regardless if you're insulating along the rafters. But I'm not seeing anything coming out nationally on it basically to say it is an issue. I do see the horror stories though in the UK like everyone else. I think the majority of it is coming down to bad installers as opposed to the system itself being bad. But as I said, I'm not a big fan of it, and I stress anyone to do their homework on it first before they go with a system like that. Yeah.
Okay, so we're just on the hour. So listen, thank you very much for your time. And as Martin said, we will be putting this recording and the slides up on the actual website and issuing it out to people in the coming days.
Yeah, perfect. Again, just to reiterate, thanks everyone for joining in, lads. Good to do these every so often. Every year we will try and do something like this. So we will pick another topic next year. If there is something very specific that you want us to cover or anything like that, do reach out to us, get in contact. We're always here to help and to offer a bit of guidance and see what we can do as well. So with that, I'll bring it to a close. So thanks everyone.